All right, and welcome to our second video in Unit 1 on functions. In this video, we're going to talk about a lot of different function types. But before we do, we're going to start with a little warm-up, just like we always do. So I've got 6 problems set up here for you. If you would take a few moments to try these 6. And again, if you can do some mental math, please do so. All right, so let's take a look at number 1 here, 15 times 13 over 5. We have a choice here. We actually have a decision. A lot of people think we have to multiply 15 times 13 and then divide by 5. But there's actually another option. The second option is to do the division by 5 first. And in this case, it's a lot easier, right? 15 divided by 5 is 3. Then multiply by 13 to get 39. So there's a little mental math strategy for you. Anytime you're multiplying by a fraction, you can divide by 5 first and then multiply by 13, or the other way if it's easier to do. Number 2 here, 6% of 11. If you take that strategy we talked about last time, 6 times 11 is 66. Obviously that's not right. Let's move the decimal back. 6.6, does that make sense? Is 6.6 6% of 11? I mean, that's well over 50% or half of 11. It's not 6%. Let's move the decimal one more place to be 0.66. That makes a lot more sense. All right, starting with 4 and add 3 until you reach 50. Really, this is that repeated addition idea behind what we call a linear function, because you're adding 3 each time until you reach 50. So hopefully that was a good little practice for you. Again, just getting back into the routine of adding numbers. Number 4, 7 times what minus 5 equals 37. Again, you can kind of fill in the blank here. You can just guess and check if you wanted to. 7 times 5 is 35. Minus 5, that's not enough, right? 7 times 6 is 42. 42 minus 5 is 30. Okay, so 7 times 6 is going to give us 42 minus the 5 is 37. So 6 is the solution there. Number 5, divide 16 by 2 as many times as you can. So 16, 8, 4, 2, 1, 0.5, 0.25, 0.125, and so on. So hopefully you're able to kind of do some of those. This actually is not repeated addition, but repeated multiplication. And I know you're probably wondering, like, well, we're dividing by 2 each time. But really, I want you to think about it not as dividing by 2, but as multiplying by 1/2 or multiplying by 0.5 each time. So we have repeated addition over here, repeated multiplication over here. And that's the difference between a linear function and what we call an exponential function, which you probably talked about last year. So let's move on to number 6 here. Simplify 150 underneath the square root there. Again, you want to separate that with multiplication and see if we can create a perfect square. So how can we rewrite 150 with multiplication so that one of the factors is a perfect square? So 4 doesn't go into 150, 9 doesn't go into 150, 16 doesn't go in. How about 25? 25 goes in, doesn't it? 25 is a perfect square. So again, one of the skills you need is your perfect squares. You need to know them, right? 1, 4, 9, 16, 25, 36, 49, 64, and so on. So 25 times, let's see, 25 times 4 is 100. So 25 times 5 is 125. 25 times 6 is 150. 25 times 6. Again, because 25 is a perfect square, we can actually evaluate that part of the square root. So square root of 25 is, I'll say this is all equal to, square root of 25 is 5. And then because 6 is not a perfect square, we can't evaluate that part. So it's going to stay on the inside of the radical. So square root of 150 is equal to 5 on the square root of 6. All right, so let's move on now to our topic for today, which is to recognize various function types and see them in real-world contexts. So instead of just throwing up some graphs and saying, here, this is a linear function, this is an exponential function, I'm actually going to give you a real-world context to start out with. And then we're going to see why the graph looks the way it does. All right, so let's begin We're going to do this through a number of different videos. So this first video, the scale here they're going to show us is from 1 to 15 along the x-axis and 0 to 1,000 along the y-axis. So alright, so what we're going to do here is we're going to see if we can map out what the water volume and how that changes over time. So over these 15 seconds, we're filling up this beaker over these 15 seconds, and how does the water volume change? Alright, so if you remember from our last video, we looked at containers and how these containers change over time as we poured in water. So we're assuming, again, a constant rate of the water coming in. And if you remember from last video, again, if there's a constant width, then the rate of the height should be constant. And so the slope should be constant of our graph here. So I'll move on to the answer here. So over these 15 seconds, you can see the water volume constantly increasing at a constant rate, about 40 or so milliliters per second. So this is just an example of a linear function in context. There are so many more examples than I can show you today, but that's just one example of a linear function. So linear functions you dealt with a lot back in integrated 1, but just to remind you of what a linear function looks like. All right, so let's move on now to our next video. So this represents population, and every single dot represents 1 million people. And we started in the 1400s as we're increasing now, but I want you to pay attention to how quickly things are increasing. Is it increasing at a constant rate, or is it maybe getting quicker and quicker and quicker and quicker? So take a look. I'm gonna stop it there. It even goes beyond our current time. But as you noticed, it didn't just continue to increase at the same rate. It got quicker and quicker and quicker in terms of how quickly the population was increasing. So you may have seen already in your mathematical career what the graph might look like here, but let's take a look. So we have population with respect to time since that since the 1400s that we started with. So it started out really, really slow, and then it got quicker and 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 quicker. And so what we have here is an exponential function. In this case, an exponential growth, because population is growing over time really, really quick. So that's just an example of how an exponential function can show up in the real world. Our next function comes to us from a video of a car driving by. So what we're going to do is we're going to think about the distance the car is from the camera. So let's think about that as the video plays. How far is the car from the camera? So it's really far away. It's getting closer. Really close to the camera, and then it goes away. We're going to assume at the same rate at which it came. And so let's think about the distance there that the car was away from the camera. So it started out, when the video started, it started out really, really far away from the camera, we'll say up there. And then as the time went on, the car got closer and closer and closer to the camera. And assuming that the car traveled at a constant speed during this video, it got closer and closer and closer. Let me use red instead here. got closer and closer and closer to the camera, and then maybe 8 or 9 seconds in, it got the closest it could to the camera here. We'll say 0 just for the sake of it. And then once it passed the camera, it started to get further and further away from the camera again. So it reached the closest point to the camera, but then it started to separate from the camera again at a constant speed. And so what we have here is what we call an absolute value graph. So this is what we call an absolute value graph. It looks kind of like a V shape, and a lot of times it represents distance away from something. And so that's just an example there of absolute value. All right, up next we have an elevator. And we're going to look at how the height of the elevator changes over time. And we're going to kind of see what function is coming out of this. So we got 12 seconds here. And this is a kind of a sped up video. So really it's over 80 seconds, but the video only lasts 12 seconds. So here we go. So the elevator goes up to all the way to the 10th floor. And then it stays there, and then it comes back down to the 4th floor, and it stays there for a minute, and then the time is up. So if you look at how the elevator changed with respect to time, you can see the graph over here. It started out at ground level for about the first 10 seconds, at least in this time span. And then after 10 seconds, it gradually increased until it reached our maximum value, going back to our key characteristics. It reached our maximum value there at the top. It leveled off at a slope of 0 for a while, and then it decreased until about 67 seconds or so, and then it leveled off, and it stayed at 4 for the rest of the time. This is actually an example of what we call a piecewise function. We talked about that a little bit last time, but this is what we call a piecewise function. It's made up of pieces. So from 0 to 10 seconds, it's made up by this piece. From 10 to about 40 seconds, it's made up of this linear function here. From 40 to 50-ish, it's made up of that line up there, y equals 10 at that point. And then from 50 to 65 or 6 or something like that, it's modeled by this linear function here. And then from 67 or so to 80, it's modeled by this function here, which is the line y equals 4. So a piecewise function, as we talked about last time, is a function that's made up of a bunch of pieces based on where you are along the horizontal axis. And if you think about it, absolute value graph is actually an example of a piecewise function. From 0 seconds to whatever this is here, 10 seconds or something, it's modeled by this linear function. And then from 10 seconds on, it's modeled by this other linear function with a positive slope, right? This one has a negative slope, this one has a positive slope. We're going to talk about that more later in this unit about absolute value functions, but just know that absolute value functions is a type of piecewise function. All right, up next, we have a video of, this is a little bit of a weird one. It's ponies in frame. So we're going to try to quantify how many ponies are in the frame at any point in time. So if you look at here, we have 15 seconds again. And then the number of ponies that we see in the frame at that moment is along here. All right, so let's take a look at the video. All right, so what do you think the graph looks like? It's a little bit of a different concept here. So let's go to the end here and let's look at the answer. So to start out, we have 1, just for a split second, half a second almost. And then from there to about 5 seconds, we have 2 in between, and we add 1 more. Then we take 3 away, and we're left with 1 at the end. So you can see here that there's 1, it adds 1 more. For between about a half a second to 4.5 seconds, there's 2 ponies in the frame. Then from 4.5 seconds to 8.5 seconds, there's 3. And then from 8.5 to 14.5, there's 4. And then for the last half second, there's only 1. So you may not have seen a graph like this before. It kind of reminds you of what we call a step function, where it steps up to a next value just instantaneously. There's no connection between the 2 graphs. So this is not what we call a continuous graph, where they're connected. You have to actually pick up your pencil to draw it. So this is again another example of a piecewise function. So because it's defined by each of those 5 pieces. 1, 2, 3, 4, and then 5 over there. All right. So another example of a piecewise. All right. Let's take a look at this one. This will be our last one. So we're measuring the height of the ball over time in feet. Goes from 0 to 3 feet. So I'm going to play the video and see if you can maybe draw a rough sketch of what the graph looks like. It actually just sits there after 4 or 5 seconds. So think about what those first 5 seconds looks like in terms of the height of that ball. All right, let's take a look at the answer.
Set, go.
All right, so as the ball bounces and comes back up, the height does the same thing. It goes down and bounces back up. And even though the ball's not really changing horizontal position a whole lot, the height is still changing. So this is not the path of the ball per se, it's simply the height of the ball. So each one of these pieces, again, this is a piecewise function, each one of these pieces is defined by what we call a quadratic function. As I said in a couple of videos ago, that's going to be the key in integrated math 2 is a quadratic function. So, like this piece right here is a quadratic function opening down, what we call concave down. And so that's what a quadratic looks like. It looks like a parabola or like a U shape, if you will. All right, so that's the end of our videos. Hopefully you kind of got a sense of where each one of these functions comes from, where it could be modeled in the real world. So let's recap here all the functions that we've talked about today. So we've talked about a linear function, which could look like this with a positive slope or like this with a negative slope. We've talked about an exponential growth. It could look like this. If it's an exponential decay, so something's decaying over time. So if you think about the natural world and how things decay over a long period of time, it could maybe be modeled by something like this. We talk about absolute value, which a lot of times measures distance. We could look like this if it's concave up, and it would look like this if it's concave down. We talk about maybe a step function. So this is maybe a more traditional step function than the one you saw in the video, where every integer has a different step that it maps to. And so it looks like steps, really. So at 0, and if you round to 0, it's going to have a height of 0. If it rounds to 1, you're going to have a height of 1. If wherever you are on the x-axis rounds to 2, you're going to have a height of 2. So that's a step function. A piecewise function, this is just one that I made up here. This one's comprised of a linear function and a quadratic function, but it's multiple pieces defined by where you are along the x-axis. And then we have a quadratic function. here at the end. And then if you have a concave down one, obviously it's going to look something, like this. So you can have one that's concave up or concave down. Again, this is going to be a huge focus in this course in Integrated Math 2. More so, some of these things towards the end, and maybe the linear functions, because that was a focus in Integrated 1. But you'll talk about quadratics a lot, absolute value a lot, exponential a lot. In this particular unit, though, we're going to focus on absolute value and piecewise functions. All right, so let's recap our goal: recognize various function types and see them in real-world context. Hopefully you're able to do that today with linear, exponential, absolute value, quadratic, piecewise, and the different types of piecewise functions. So with that, I'll say goodbye, and I hope to see you next time.